Welcome to today's paper reading. Today's paper is titled, Watch Your Steps, Local Image and Scene Editing by Text Instructions. This paper was published on AR14 by Mirzaei, Brubaker and colleagues from Samsung AI Center Toronto and University of Toronto. The research aims to identify key challenges in the field and develop innovative solutions to improve efficiency. An experimental approach is used, along with advanced data analysis techniques and comparative studies. The expected outcomes include enhanced performance, cost reduction, and the implementation of sustainable practices. Figure 1 provides an overview of the relevance map calculation process and its application in guiding image and neural radiance field (NERF) editing. The relevance map is derived from the discrepancy between noise predictions made with and without the textual instruction. This map is crucial for localizing the edits to the most relevant regions of the image or scene, ensuring that changes are confined to areas that are most pertinent to the edit text. The left inset illustrates the calculation of the relevance map, while the top right and bottom right insets showcase sample outputs of image and NERF editing, respectively, all guided by the relevance map. The core of our method lies in the use of relevance maps, which are generated by identifying the discrepancy between InstructPix2Pix predictions with and without the text instruction. These maps serve to localize the regions in an image that need to be edited, ensuring that only relevant pixels are modified. For 3D scene editing, we extend this concept by training a relevance field on the maps from training views, which helps in maintaining 3D consistency during edits. Our approach not only achieves state-of-the-art performance in both image and NERF editing tasks but also ensures that the original input's integrity is preserved. In the realm of diffusion models, significant advancements have been made in high-quality image synthesis, enabling the generation of images from text descriptions. These models have also been adapted for image editing based on textual instructions. However, challenges such as over-editing and the inability to maintain original image details persist. Similarly, neural fields, particularly NERFs, have seen improvements in speed and rendering quality, sparking interest in editing tools. Yet, current editing methods are often limited to simple scenes or specific tasks, and suffer from spatial ambiguity and view inconsistency. These limitations motivate the need for more precise and consistent editing methods. Figure 2 provides an overview of a denoising step in relevance-guided image editing. The process begins with the creation of a relevance map, which is then binarized to form an edit mask. This mask identifies the regions of the image that should undergo editing. Following this, the output from the last denoising stage is processed using IP2P. Crucially, the unmasked pixels, which are not intended for editing, are swapped with the corresponding pixels from the noisy input. This ensures that the integrity of the original image is maintained throughout the editing process. The use of IP2P in the denoising step is key to achieving accurate and localized edits, while preserving the overall consistency of the image. Neural radiance fields, NERFs, represent a 3D scene as a neural field that maps a 3D coordinate and a view direction to a color and a density. This field is optimized using multi-view posed image sets and is rendered using a volumetric rendering equation. On the other hand, InstructPix2Pix is a model that edits images based on text instructions. It uses a latent diffusion model where noise is added to the latent representation of the image, and a denoiser is fine-tuned to minimize the diffusion objective. The strength of the edit can be controlled by image and text guidance scales, allowing for precise image modifications. In this section, we describe the method used for relevance-guided NERF editing. First, we calculate the relevance map by adding noise to the encoded image and predicting the noise using IP2P. The absolute difference between the predicted noises is used as the relevance map. Next, we guide the image editing process using this relevance map. An edit mask is created based on the relevance map, and the denoising process is guided by this mask to produce the edited image. Finally, we extend this concept to 3D scene editing by introducing a relevance field. This field ensures consistency in the localization of edits across different views by iteratively updating the training views. Figure 3 provides an overview of our relevance-guided NERF editing method. The The process involves iteratively selecting a random view and rendering it using both the main NERF and the relevance field. The rendered image is then edited, guided by the rendered relevance, to only modify pixels that are highly relevant to the task. The IP2P method 6 serves as the backbone of this editing approach and is always conditioned on the initial captures from the scene. This conditioning is crucial to prevent significant deviations from the original scene during the recurrent synthesis process. 15. The Relevance Guided Image Editing Module, as described in Section 4.2, returns an edited image and an updated relevance, which are subsequently used to update the corresponding training views for both the NERF and the relevance field. The experiments were conducted using datasets specifically designed for image and NERF editing. For image editing, a dataset of 5,000 images paired with instructions was used. For NERF editing, 14 different tasks were evaluated using scenes from IN2N and LFF. The metrics employed to evaluate the performance include clip image similarity, which measures the similarity between the edited and original images, clip text image direction similarity, which assesses the agreement between the change in images and text captions, and NIC, a no-reference image quality metric. The baselines compared against include state-of-the-art methods such as diffedit, SDedit, and IP2P for image editing, and IN2N, NRFArt, IN2N with stable diffusion, and score distillation sampling with IP2P for NERF editing. Figure 4 presents a quantitative evaluation of image editing methods, focusing on text-image direction similarity and fidelity to the input image. The x-axis represents the text-image direction similarity, while the y-axis indicates the fidelity to the original input image. Our model demonstrates superior performance in achieving higher text-image direction similarity while maintaining a higher level of fidelity to the input. The text guidance parameter is set to 7.5 for all methods. The strength of SDedit is varied from 0.1 to 0.9, and diffedit's encoding ratio is adjusted between 0.5 and 0.9. For IP2P, the SI parameter is changed from 1 to 2.2, whereas for our method, SI is fixed at 1. The figure also highlights the impact of the mask threshold, tau, on image similarity, showing that increasing tau initially improves image similarity, but excessively high values can negatively affect the edit success. Figure 5 presents a comparison of our image editing results with those of IP2P. Both models use the same settings for text guidance, SD, and image guidance, SI, set to 7.5 and 1 respectively. However, IP2P demonstrates a tendency to over-edit, failing to isolate the specified region for modification. In contrast, our model effectively predicts the scope of the edit and confines the changes to a specific region, thereby maintaining higher fidelity to the original input image. This localized editing approach ensures that only the necessary areas are modified, preserving the integrity of the rest of the image. Figure 6 presents a comparison of our image editing method against two other methods, diffedit and SDedit. Diffedit, which necessitates both input and output captions, struggles with the complexity of captions in the IP2P dataset. Conversely, SDedit shows improved performance when provided with the output caption. Our model excels by closely adhering to the instructions while preserving the coherence with the original input. This ensures that the edits are precise and only applied where necessary, resulting in outputs that closely resemble the inputs. For more examples, please refer to the supplemental materials. Figure 7 presents qualitative outputs of our NERF editing method. It includes multi-view renderings of edited NERF for 3 different scenes, each with a specific text instruction. The figure demonstrates that our method successfully follows the text instructions while maintaining view consistency and keeping regions less relevant to the task intact. This showcases the effectiveness of our method in scene editing while preserving the integrity of the scene. Figure 8 compares our scene editing method with IN2N 15. The relevance field allows us to focus edits on the most significant regions, reducing the decoder's spatial ambiguity on unedited pixels. This approach enhances view consistency in the edited areas, as smaller edits are more likely to result in consistent outcomes across views. Additionally, maintaining a low nerve reconstruction loss outside the mask improves convergence within the masked region. Figure 9 illustrates a comparison of our scene editing method with NARFART and IN2N. The baseline methods modify the background, shirt, and hair of the person, potentially compromising scene semantics, such as the individual's identity. In contrast, our model focuses on minimal necessary changes, specifically editing only the eyes and ears. This approach ensures that the desired semantic alterations are achieved without unnecessary modifications, preserving the integrity of the scene. Figure 10 presents a qualitative comparison of our scene editing method against two baselines. IN2N with stable diffusion, SD, performs iterative dataset updates similar to IN2N, but substitutes IP2P with stable diffusion. SDS with IP2P updates the nerf based on the SDS loss calculated through IP2P. Our method notably results in sharper outputs, contrasting with the baseline methods that have failed to achieve the same level of sharpness in the task. Figure 11 presents a comparison of relevance maps calculated using various noise levels and a rendered relevance from a relevance field. The study identifies TREL equals 0.8 as a reliable noise level for relevance map calculation, ensuring the denoising process focuses on global image structure rather than fine details. This approach results in relevance masks that encapsulate global boundaries of relevant regions. Additionally, the rendered relevance field, supervised by maps from multiple views, effectively acts as an ensemble, providing a more accurate representation. The NERF architecture's inductive bias limits high-frequency field variations, leading to smooth consensus relevance renders with minimal noise. Figure 12 illustrates the failure cases of our image editing model. The model heavily relies on IP2P for predicting the relevance map and the edit. Despite our model's ability to outperform IP2P by localizing the edits, it is unable to recover from IP2P's catastrophic failures. For instance, in the first example, the prompt change to a rose resulted in unnecessary changes to the background and hair color. The relevance mask superfluously highlights these areas, indicating the model's failure to accurately localize the edits. In the second example, the prompt had a cat led to the replacement of the person and the dog with cats, demonstrating the ambiguity in localizing the edit with respect to the prompt. These examples highlight the model's limitations due to its dependency on IP2P. Table 1 evaluates our scene editing model against IN2N and per frame IP2P in terms of clip text image similarity, frame similarity, edit similarity, image similarity, edit PSNR, and Nike. Our model achieves similar text-image similarity scores to IN2N and IP2P, indicating successful matching of edited scenes to output captions. However, IP2P's independent view editing results in lower consistency compared to our method and IN2N. In terms of image quality, our model outperforms IN2N by producing sharper and higher quality renderings, despite IP2P's higher Nike due to lacking typical NERF artifacts. In this study, the authors propose a method to predict the relevance of each image pixel to an editing task based on a text instruction. This is achieved by examining the discrepancy between a conditional and an unconditional pass over a diffusion-based image editor. The relevance is used as a mask to guide the generation process, ensuring that unmasked pixels remain unchanged, thereby enabling localized image editing. Additionally, the authors demonstrate that training a relevance field on the relevance maps of the training views of a NERF can achieve similar localized editing effects in 3D scenes. The method shows superior performance compared to existing baselines in both image and scene editing tasks. Thank you for watching.